All right, it is 2, so we will get started. We have a little bit to finish up from Wednesday, finishing up with DNA, and then we will move on to amino acids and proteins. So the last thing we talked about on Wednesday was this idea of where to get DNA if you want to do some molecular cloning, and one place you can get is this DNA library. Now, after we have a plasmid and after we have our sequence that we want to clone, and we have inserted our sequence into our plasmid by using restriction endonucleases and using ligases, the next step that we want to do is that we want to use PCR to replicate our plasmid with our sequenced DNA. PCR stands for polymerase chain reaction, and it's a method developed about 30 years ago now, that actually 40 years ago, it's 2021, so 40 years ago now, where you can use some pretty fancy techniques to replicate DNA extremely fast and more or less in an accurate manner. So on the left here is the sequence of the PCR steps. So here, let me get my pen out. All right, so here, wrong mode, sorry. Here we have our target DNA that we want to copy, and we have primers. What a primer is, it's just a short sequence of DNA, and these will dictate where we want to copy. These are the beginning and end points of the sequence we want to copy. So the first thing with PCR is that you add your DNA to be copied, your primers, you add your nucleotides, so ATP, CTP, TTP, and GTP. You add your enzymes that will replicate the DNA, which is DNA polymerase, and you add some salt and you're ready to go. First step, you let the machine, and the machine that does this, if you've never heard of it, this is all done in a thermocycler. And what a thermocycler is just a simple machine that can do steps of heating and cooling in a repeated manner. You just program it to do that. And so the first thing you want to do with your thermocycler is have it heat up to 95 degrees centigrade. When you heat DNA this hot, what will happen is that the duplex will unwind and it will separate. Once the DNA separate, then you can cool down the thermocycler to roughly 55 degrees centigrade. What this will do is that it's cool enough that your primers will attach, or as we call it, anneal, to your target DNA. Then you raise the temperature to roughly 72. This temperature allows your DNA polymerase to work, and you will lengthen your new DNA, or you'll create new DNA based on where your primers start. And we're going to go through like a whole little PowerPoint movie to actually show how this works. So PCR is really good for amplifying DNA, but what else PCR is really good for is causing mutations. So here in this image on the right, that's what we're showing here. So the green is our gene that we're going to mutate, and our little pink here is our primer. And what you can do is that if you incorporate some mismatches into your primer, but overall it's still pretty good, your primer will still attach to your target. Then when you go through the PCR cycle, you can see here we have CGT, when we do our replication, across from this C, we're going to put a G. Across from this G, we're going to put a C. Across from this T, we're going to put an A. So we're going to change what the gene is in a way that we can control. So this is a way that we can do mutations. And this is a huge technique when it comes to biochemistry, because a lot of the times when you want to understand how a protein works on an amino acid basis, you will do PCR with different mutants. You will cause different mutations, see how those mutations affect the protein, and by doing that, you can learn how the protein works. All right, so is there any questions about PCR or the information I went over there? All right. So let's go through PCR, the movie. So this will give you like a visual idea of how PCR works. So we start with our DNA, our 5' 3' DNA that we want to duplicate. Round one, we heat to 95, so they separate. We cool to 55, and now our primers have attached. We heat up to 72 and let the polymerase work, and now we have duplicated some of our DNA. Now, after one round of PCR, the amount of DNA that we now have is 2 to the power of 1. By star DNA means DNA that has been copied 100%. So originally, when I do this, get my spotlight back out, I want this whole DNA strand to be copied, 5' to 3'. However, my first round of PCR, I have not copied that whole strand yet. So that's why I say I have 2 non-star DNAs. I have 2 copies of DNA, but they're not what I want. My star DNA is my completely copied DNA. The mathematical formula for this is 2 to the power of how many cycles minus 2 times how many cycles. So far, I've gotten 0 correctly copied DNA. That's fine. I've only done 1 round of PCR. So next round of PCR. Melt, anneal, extend. Round 2, 4 DNAs, but still, they're not the DNAs I want. So I have 4 non-star DNAs, 0 star DNAs. That's fine. Let's do PCR again. Melt, anneal, extend. Yay! I have 2 DNA, finally. So after 3 rounds, I have 8 copies of DNA now. 6 of them is not what I want, but finally after 3 rounds, I got 2 DNAs that have been copied completely. They're what I want. Round 4, melt, anneal, extend. Okay, now we're getting somewhere. After 4 rounds, you're up to 16 DNA. Half of those are not what I want. Half of those are what I want. So after 4 rounds, we are at 50% of our DNA is just the fragment that I want. And instead of doing this movie a bunch of times, here's just the results. And let's jump all the way down to 10 cycles. So after 10 cycles, I've made 1,024 copies of DNA. 20 of these are not useful to me. 1,004 of them are my correctly copied DNA. So you can see how exponentially we just grow the DNA we want to copy, or the sequence in the DNA we want to copy. And normally in PCR, you do this like 30 times, right? You do 30 cycles and you end up with millions and millions of copies of the DNA that you want. While the non-star DNA will still be a very short amount. All right, so to make sure we understand PCR, I have some questions. I will actually answer the first one because we have not talked about it yet. So my first question is, when we're making primers for PCR, what are the ideal characteristics of the primers we want to make? Well, generally, your primers, you want them to be roughly 18 to 22 nucleotides long. Any shorter than that, they're not going to be specific enough. When they become too long, they might have trouble competing against the other DNA for sticking because they're just too long to stick. So you want a good size like that. Also, when they get too long, another problem is they will interact with themselves, which isn't good. So usually anywhere from 18 to 22 nucleotides. Usually you want their melting temperature to be somewhere between 52 and 58 degrees C. And you usually want their G to C content to be anywhere between 40 and 60% GC. These two things are really the same thing because the more G and C's you have, the higher the melting temperature. The lower G and C's you have, the lower the melting temperature. Because remember, G and C have 3 hydrogen bonds, A and T has 2 hydrogen bonds. Now, if you ever find yourself in a situation where you do need to make primers, there are websites available that'll tell you if your primers are good or not. They will check for all of these things, and they'll let you know before you actually buy primers. Are these primers going to be very viable in your experiment? So those are the ideal primer characteristics. Here in my other questions down here, I'm going to give you some time to think about these, because if you can answer all 4 of these questions, you understand how PCR works 100%. So test yourself on these. So I'm going to give people a few minutes to think about these and what outcomes would happen in our PCR experiment in these different scenarios. So if you have questions, let me know. Otherwise, I'll give you a few minutes to try and answer these, and I'll be back with the answers in a little bit. All right. Hopefully you had some time to at least do a couple of these and think about how the primers in DNA work in PCR. So let's go over these. So what happens if one of the primers aren't added to your mixture? So let's draw this out. So let's assume I already separated my DNA. And then I add my primer. What's going to happen is that only one strand of DNA will ever replicate. We would never be able to replicate this strand of DNA. So your PCR would be a failure because you only get one strand that is replicating over and over and over again. So that's a problem. So you need both primers to replicate on both strands. So that's A. How about B? You have one primer that can attach to multiple places. Well, that will be an issue because let's say you have a primer that attaches right there, a primer that attaches right here. Well, it's the same primer. It's just attaching at different spots. So you're going to get DNA of different lengths now. So extension. Well, actually, let me redo this. The maroon place is going to extend all the way out here. Where attached where the dark green is going to extend all the way out there. And your blue will extend out here. So here we're getting DNAs of different lengths, which will overall decrease your star DNA that we talked about in the movie. So your PCR could still work, potentially, but it will probably fail. You'll probably not get the results that you want. Just because the DNAs that you're making are all different lengths, and your polymerase might not actually be able to work because it's going to run into these replicating DNA strands, and that can cause an issue. All right, C. C is I have a single strand break. Okay, let's see what happens here. So C, let's say I have a break right here. 5 prime, 3 prime, 3 prime, 5 prime. Okay, and let's think about this. So if we have primer that will attach here, primer that will attach here. So during our first replication, we're going to make this, then we're going to make that. So that's what replicates after round 1. So after round 1, we did replicate DNA down here. That's good, but we didn't replicate the top strand. So let's go to round 2. Well, round 2, as long as one strand was all right, it should be fine. Because you can see that this is actually a complete DNA. We have fixed our single strand break in our maroon DNA. So actually, if you just have a single strand break, so here I'm going to put the primers again, replicate. If you only have a single strand break, that's no problem. Because due to the nature of DNA, when you create that first replication, you're going to fix the single strand break in your daughter strand. However, if you have a double stranded break, that's a problem. So if my break is like that, I'm completely just missing that section of my DNA. I can never get that back. So if I do PCR, and I get something like that out, where I make double-stranded DNA, I can never regain the place that's missing if it's broken in both strands. This will forever be a mystery to me because I have no template to mix it. So this is a failure. So by doing this, A, B, C, and D, hopefully you can see, how the primers and how the DNA interact with each other. And I think that's a very good thought experiment of working through the different steps of PCR and figuring out what exactly would be your results if any of these situations happen. So is there any questions about this problem or anything at all about anything we've talked about so far? All right, let's move on to amino acids then. Moving on to proteins. The meat of this class is going to be proteins. All right, so proteins are made out of amino acids. So amino acids is the monomer, proteins are the polymer. And we have 20 standard amino acids we're going to use. Some people say 21, I say 20. All of these amino acids are called alpha amino acids. And they all have this general layout where you have a central carbon called the carbon alpha. And attached to that, you have what we have R. R is any of our 20 side chains. So the side chain, basically that R group, determines what our amino acid is. And then we have NH2, really that should be NH3, and COOH, really positive. That should be COO minus. When you look these up on the internet, you will often find your amino acids being NH2 and COOH. Inside the cell, they're like never that. They're always charged. So this R group, we call it the side chain. These three molecules that are connected, we call that the backbone. So if you ever hear me talk about the backbone of an amino acid or the backbone of a protein, I'm talking about the atoms I just put in a box. That's the backbone, right? Now, like I said, under cellular conditions, these things will be charged. So these are called Switzer ions. Zwei is the German word for two. So basically this is two ions, which it is, Na3 plus, COO minus. All right, and so what do you need to know about amino acids for this class? Well, many things, but what you need to know is the full name of each amino acid. You need to know the three-letter code of each amino acid. You'll need to know the one-letter code of each amino acid. So each amino acid has three different names: the full name, three-letter code, one-letter code. You need to know what the side chain looks like. If the side chain has a pKa, you need to know that. You need to know that all N-terminal pKa's, we're going to just say it's roughly 9.4. I'll put a sheet up on Blackboard that has all this information laid out for you. But on that sheet, you'll see that all the N-terminals are different for their pKa's because it does matter what's on your side chain, what the pKa of that nitrogen is. But it's really not that important to know each individual number. So we're just going to say all N-terminal pKa's are 9.4. And we're going to say all C-terminal pKa's are 2.2. So I know that is a lot, but amino acids, they're going to be our vocab moving forward in this class. I'm going to be talking about proteins. I'm going to be talking about specific amino acids in our proteins. And I'm going to need people to be at the point to think about those amino acids just by word association instead of looking them up each and every time. To really move at a pace, I'm going to need people to know what I mean when I say aspartic acid or glutamic acid or glycine or tryptophan. So yeah, for studying these, repetition is the best. On the videos, I made some stupid I made a fool of myself to help you memorize those. There are a lot of things out there because like anybody who takes the MCAT has to do this, or any of those random cat tests, you have to know the amino acids. So there's a lot of resources out there. I'm sure if you look it up on your phone, you can find like apps to help you study the amino acids. So yeah, just take it, every day, do a little bit, and you'll get these memorized, no problem. So when we talk about amino acids, we generally don't care about amino acids by themselves. We care about amino acids when they are formed together. And so the reaction where we combine amino acids, we take one oxygen from our C terminus. That's what these are called, by the way, C terminus. So I'm going to put C term and N term. We take one oxygen from the C terminus of one amino acid plus two hydrogens from the other N terminus of the other amino acid, and we make H2O, which is called a condensation reaction, which makes sense if you remember from general chemistry. Condensation is where gas water, or water vapor, I guess, turns into liquid water. Well, here we're creating liquid water by combining amino acids together. This reaction is reversible with an enzyme, and the reverse is called hydrolysis. Now, anytime you see the word like lyse, I think I've forgotten a lysis, L-Y-A-S-E, I believe it is. Anytime you see the word lyse anywhere in this class, that means to cut. So hydrolysis, hydrolyse means water cut. So to break the bond we just formed, water is going to come in and cut that bond to reform our separate amino acids. Now, when we do form a new bond, that is called the peptide bond. So between the old C terminus and the old N terminus, this new bond is always called the peptide bond. So when you combine two amino acids together, you get a peptide bond. And when writing amino acids or anything to do with proteins, you always read it N terminus to C terminus. Just like how we went from 5' to 3' in DNA, here we're going from N terminus to C terminus. Now, if we look, so this is just a simple dipeptide. Down here, we have 4 amino acids. So here we have, and it's cut off, but alanine, tyrosine, aspartic acid, and glycine. So every time we've combined one of these, we form a new peptide bond, right? N terminus, C terminus, then our various R groups. And to make a protein, you combine 100 amino acids. You combine a lot of amino acids. So I do have a question, and this is a critical thinking question. So I'm going to see if anyone here can use the power of their brains and answer this. So tyrosine is shown right here. This is tyrosine. So if it's in a free amino acid, that is, if tyrosine's not in a peptide bond, it will be barely soluble in water. Therefore, if I make a peptide that only has tyrosines in it, do you think these tyrosines will be more soluble in water or less soluble in water compared to a single amino acid? So does anyone have any ideas? If tyrosine itself is somewhat soluble in water, if I put many tyrosines together, do they become more soluble or less soluble? You think less, but you're not sure why. So you're correct on less. It does become less soluble. And to think about that, to bring that thought out one more step, we need to think about the structure, right? How is the structure of a single tyrosine? Different than a peptide of tyrosines. What do we lose when we go from the single amino acid to the peptide? What goes away? Water. That's correct. What else? So let's say I have this single tyrosine. Let's say, actually, let me say I have two tyrosines, and I'm going to combine them into a peptide. Maybe this will show you what I'm talking about. Okay, so I have my two tyrosines. I'm gonna add them together, and I'm gonna draw it over here because I'm running out of space. And C double bond O, and H, C double bond O minus, plus hydrogen, 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 CH2 ring, CH2 ring. The lone hydrogens, correct. But what, how to put this without giving it right away? The charges, yeah. So single tyrosine, if you look at the single tyrosine, you all were hitting on it. So it was very hard for me to like exactly get what I was talking about without just saying the charges. But you're right, water, the hydrogens, that all equals the charges, right? So a single tyrosine, you see it has a positive and a minus charge. These charges help to make it soluble in water because you have this big old phenol group. Phenol generally does not interact with water that well because there's a bunch of carbons and hydrogens. So when I have two single tyrosines, I have two positive charges and two negative charges. However, when I combine them together, I lose a positive charge and I lose a negative charge. And you can expand that out to, like, if I had, let's say, 100 tyrosines in the single amino acid form. So single amino acid, SAA. overall, each one of those tyrosines would have a positive charge. So I'd have 100 positive charges, 100 negative charges. Whoops. Okay, now let's take that tyrosine and we're going to make that into peptide bond form. I'm going to combine all these tyrosines together. Now I have one positive charge from the N terminus, one negative charge for the C terminus. So you can see if it's just tyrosine, you lose a lot of charge. So that's why they become less soluble in water when you connect them versus when they're by themselves. All right, any questions about that idea? All right. So it is very important for us to understand how amino acids combined and what amino acids look like. So I'm going to give everybody a few minutes here. And it's fine if you want to look up like an amino acid chart. Like I said, I'm going to put one up on Blackboard after today. But try and draw the pentapeptide tapes. So get out a piece of paper, try to do that, and I will draw it for you in a few minutes after I let you look at some amino acids and try to draw it. All right, so hopefully you had some time to at least, make a couple peptide bonds here. All right, so let's do tapes. Always start with the N terminus. So N terminus. And the way these amino acids go, it's always N, C alpha, carbonyl. Then N, C alpha, carbonyl. Off these C alphas are going to be your R group. So N, C alpha. And on the C alpha, you don't have to put the hydrogen. It's usually just implied. So threonine looks like that. And there is a hydrogen off there. Usually I don't draw that hydrogen. The way I remember threonine, one of the ways is that it kind of looks like a lowercase t. And I pair threonine and cysteine in my head because cysteine looks very similar, except it ends in an sh. It's not the one-to-one. Threonine's an OH. So C double bond O, and H, C. Then we have alanine. So this is T, A. Alanine is the easy, one of the easiest. The side chain is just a methyl group. So alanine, CH3, C double bond O, N, C. Okay, proline is the weirdest amino acid to me. Proline is the only amino acid that binds to the backbone. So the side chain actually comes up and binds to the backbone. And you can see when you do that, there's no hydrogen. So there's no hydrogen connected to that nitrogen because proline's backbone just comes up and binds it. So that's our C alpha, C double bond O, and H. Next is glutamic acid. I think I said this in the video, glu-E. And the way I remember this is with a partner, is with aspartic acid, but let me draw it. So CH2, CH2, C double bond O. The way I learned this was kind of dumb, but I memorized that both D and E, so aspartic acid and glutamic acid, so asp, glue, they both ended with C double bond O. They are both my negative amino acids. The only difference is the total number of carbons, right? So D, I always remember that as di, as in 2. So aspartic acid in its side chain has a total of 2 carbons. E, which is 1 letter further than D, so since it's 1 letter further, it has 1 more carbon in its side chain. So it has 3 carbons in its side chain. And feel free to come up with your own stuff or look at people on the internet. There are a ton of examples how to memorize these amino acids. That's E. And then C double bond O and H. And then we have our friend serine. So you got threonine, which has a CH3 off of it, and then an OH. You have cysteine, which just has an SH, and you have serine. So serine, cysteine, and threonine. They all kind of end the same. All their side chains are similar. You have a carbon alpha. Serine has an OH at the top. Cysteine has an SH. Threonine has a CH3 and an OH. So I've always memorized those as like a set for some reason. Then that's our last amino acid. So don't forget your C-terminus. So that is the pentapeptide tapes for you. So is there any questions so far about our amino acids, about our peptide bonds, or anything up to this point? All right. Now, we are dealing with amino acids. So these are acids, and they do have pKa's with them. We did talk about pKa's at the beginning of the semester, and they have to do with protonating in deprotonating. So usually all amino acids have 2 to 3 ionizable groups. They will always have 2 because that's the N term and the C term. Some have 3 ionizable groups. The ones that have ionizable groups are D, E. These are your negative amino acids. R, K, H. These are your positive amino acids. Y, tyrosine can also be it. And tyrosine is usually neutral. So when I say negative, positive, or neutral, I mean at pH 7, this is what the amino acids are, but at different pHs, they can change. So thinking about what the charge is of these amino acids based on pH, if we go to the extremes, at pH 1, every ionizable group has a proton attached to it. So the N terminus must be charged, and the C terminus, which is usually negative, becomes neutral. So at a low pHs, the backbone has a positive charge. So these are our backbone atoms. At very high pHs, everything gets deprotonated, right? So keep that in mind. Low pH means lots of hydrogens around in solution, so everything gets protonated. High pHs, very few protons are around. Everything becomes deprotonated. So for the backbone, we have COO minus, so it stays minus. NH2, the N terminus, loses a proton, so it becomes neutral. So the backbone is negatively charged. If you're not at either very low or very high pHs, the calculation becomes a little more difficult. In general, though, if your pH is above your pKa, you are unprotonated. So, for example, our C terminus, we said that the pKa of the C terminus is 2.2. Inside the cell, pH is 7. So at cellular conditions, our C terminus is unprotonated. That's why I said it's going to have a negative charge. It already lost its proton. While if pH is lower than our pKa, so the N terminus, the pKa, could be 12. Inside the cell, the pH is 7. So that's why the N terminus is always protonated at cellular conditions, because the pH of the cell is lower than the pKa. And by knowing pKa's, we can actually calculate what's called the isoelectric point, or PI. The isoelectric point is the pH when the molecule has no charge, where overall it's neutral. PI will matter. That should be, pH word. The PI will matter a lot when we talk about purifying proteins in experiments. But just know that PI is the pH of what you're neutral at. And we can calculate this for amino acids. It's relatively easy. So for any amino acid that's neutral at a pH of 7, that's what I mean by neutral. The pKi is simply, the equation you use for Pi is here. Pi equals 1/2 pKi plus pKj. So the pKi is just whatever your N terminus pK is. C terminus, whatever, or rather your pKj is what the C terminus pK is. Neutral amino acids, super simple because their side chain can't become charged. For negative amino acids, it's a little bit harder. Not much though. The pKi is your C-terminus. pKj is whatever your side chain is. For positive amino acids, that is positively charged at 7. So this would be R, K, sometimes H. This would be D and E for negatively charged. Your pKi is your side chain. Your pKj is your N-terminus. For real proteins, like proteins that are made out of 100 amino acids, it's hard to calculate that. You can. Computers can do that. The best way to figure that out is experimentation, though, because each protein will be slightly different just on the way it folds in its 3D structure. All right, so I know that was a lot of information on a small slide, but does anyone have any questions off the top of their head that they want to ask about this sort of thing? Or anything at all that we talked about? All right, so Monday, we're going to figure out the charges of different peptides at different pHs. So we're going to work through how to do this. Normally, every single year I've taught biochem, this is one of the issues or one of the problems that's given students the most issues. So we're going to spend a good amount of time on Monday to try and do this. So definitely make sure you're paying attention for this part. We're going to tackle that first thing Monday. Otherwise, I will put up in a homework assignment like always. If you have questions over the weekend, don't hesitate to reach out. Otherwise, I have nothing left for you. Shall we know how to get PI? Yeah, you should. So you should be able to use that equation to calculate PI for amino acids. And the PK, the PKI, PKJ, those are things that that's one of the things I'm gonna ask you to memorize, in that we're gonna say all N-termini, get rid of all these stars. We're gonna say all N-termini pKa are 9.4. So that's always 9.4. This is always 2.2. And you just need to know the pKa's for the side chains. So I'm going to have questions on the test. And by the way, if you aren't aware, the test is 2 weeks from now, I believe, 2 weeks from today. I'm going to have questions on the test where I just asked you, for this amino acid, what's the pKa? And like I said, I'm going to put up that sheet. But you should be able to use this equation to figure out PIs. And I think I do have a couple of homework questions that have this in it. So you can get practice doing that before the test. But yeah, you should be able to use that equation. All right. Well, if there's no other questions, I don't have anything else for you. So if you do have questions, let me know. If you want extra tutoring sessions, let me know. I'm always available. Otherwise, hope you have a good weekend, and hopefully I'll see you Monday. Have a good one, everybody.